Another operation we can do is something called the cross product, and this can only be done in R3, so you can only have three-dimensional vectors. Now the cross product geometrically, it's a way of getting a vector that's perpendicular to whatever you're taking the cross product of. So this cross product is actually giving us a perpendicular vector to both u and v, and that's why we need that third coordinate. If you imagine having two vectors here, u and v, and you want a vector that's perpendicular to it, you need to imagine that this vector is coming out at you. You would need a vector like that. Okay, so we need a third dimension there. In any case, this is how we define the cross product. If you know matrices, the cross product can be defined in terms of the determinant of a matrix, where the first row is the standard basis vectors, the second row is your first vector u, or the coordinates at least, and the third row is the coordinates of the second vector. If you don't remember matrices, we'll get into that a little bit later. You can jump to this line right here, and that's the formula for it. Okay, so this is how we define the cross product. So a couple of properties, and we'll see some of them are similar to the dot product, some of them are not. First one is definitely not. Notice that u cross v is not v cross u, it's actually minus v cross u. So we're not getting that nice, the order of the cross product does matter. Okay, we do have a distributive property though. So if you're taking the sum of two vectors and crossing it with another vector w, you can distribute the cross product. Okay, notice we have the cross product here. You can also pull out scalars. Okay. If u and v are parallel, so not perpendicular, if they're parallel, we have that their cross product is going to be the zero vector, which is pretty nice. Now number 5 should look familiar. This is kind of the analog for the dot product property we were using up above. So the length of the cross product is equal to the length of u times the length of v, but instead of cosine, we have sine for the cross product. And then lastly, u cross v is perpendicular to both u and v, and that's by construction. There are two other geometric results for the cross product that I want to talk about. First of all, the cross product actually gives us a way of calculating the area of a parallelogram. So let's suppose that we have two vectors, u and v, like this. Okay, then I can finish, and let's pretend like these are perfectly straight vectors here. Let's finish the parallelogram, or complete the parallelogram, kind of like what we did when we added vectors. Okay. And now this gives us a parallelogram here. Now, what is the area of a parallelogram? Remember, the area of a parallelogram is base times height. Okay, and if you're curious how you come up with that, it's really geometry. You can think about a parallelogram as two triangles, okay, which are the same triangles, by the way, and a rectangle. And if you calculate the area of this rectangle here and add up the two triangles here, you'll actually get base times height. It's a really, really cool geometrical argument, which I recommend you doing. But in any case, we're going to take this as given. The area of the parallelogram is base times height. Now notice that the base in this case is just the length of the vector v. Okay. Now the height we have to work on. So the height is this distance right here. Now using SOHCAHTOA, but now we're going to use the SO part. Okay. We know that sine of theta is equal to, so the height here, over the length of u. So that means that height is equal to the length of u times sine of theta. And using our equation 5 here, or formula 5, and reshuffling things, we get that h is really, okay, solving for u and sine of theta, it's the cross product divided by the length of v. Okay. So substituting that into our equation here, okay, we get that this is cross product over the length of v. Notice that these lengths cancel out, and we get u cross v. So notice what this is telling us is that the area of the parallelogram spanned by u and v is actually just the length of their cross product. A crazy awesome geometrical interpretation of the cross product. The last thing I want to talk about, you can, and you can read this in a little bit more detail in your book, but we can talk about the area of a parallelepiped. And I hope I'm spelling that right. So let's say we have U and V as drawn here, and we have another vector W, which we'll draw sort of like this. So here's U, here's V, here's W. Then the parallelepiped is sort of like the box that's generated from these three vectors here. I recommend definitely going into your book and then seeing the actual picture. But in any case, that's a parallelepiped. It's kind of like a box that's been tilted forward. Now I'm sorry, I shouldn't say area, by the way. I should say volume because it's three-dimensional. So the volume of a parallelepiped is actually given by the length of, the absolute value of U cross V dotted with W. Okay. If you want a more detailed explanation, go ahead and look in your book. But that's also another fascinating result of the cross product. And this is actually a nice way of combining the cross product and the dot product. We call this I think it's called the scalar triple product. But in any case, if we do this product here, we actually get a nice geometrical result that it's the area of this